In this video, we continue our look at ellipses, and we're going to start with kind of an interesting application problem. So it says here that the ceiling of a whispering gallery has the shape of a hemi-ellipsoid, with the highest point of the ceiling being 15 feet above the elliptical floor and the vertices of the floor 50 feet apart. So now an ellipsoid is just a three-dimensional version of an ellipse, right? So kind of think like an egg, but an egg that's actually, symmetrical. A hemi-ellipsoid would be half of an ellipsoid. And so in a whispering gallery, there's a number of these that exist in various cities. The idea is that if two people stand on the foci, then they will be able to hear each other perfectly because sound waves emitted from the foci will be directed toward each other, right? Because remember that when we have an ellipse, just to draw one real sloppily here, but when you have an ellipse, the idea is you create it by doing this, right? We use this analogy of you kind of take a string and you stretch it out, and then keeping the string tight, that's how you sketch out the ellipse. Well, now what we can do is we can kind of think of these 2 points and this string instead of as being sound waves, right? So if you talked, then your sound should go up here and then bounce off and go right to the other focus. So that's kind of the idea there, right? So let's sketch a picture, a simple picture of this hemi-ellipsoid. So we'll just do kind of a side view of it. Okay, so what I'm going to draw here is just kind of the floor, and then we'll draw the top half of an ellipse. So just imagine we're looking into this room from the side, is the idea here. And so what they're saying here is, hey, we put a person here. We put a person here, and they are at the foci, then they should be able to talk to each other really quietly, but the sound waves will bounce to the other person so perfectly that they'll be able to hear each other. So we know, right, what are we going for? We're going for an equation that looks like this anytime we're talking about an ellipse. And then what we need to do is remember the relationship between this A, this B, and the foci. So remember that C squared is equal to A squared minus B squared. Right? Ultimately, they're asking us how far apart are these two people standing? Okay, but what we can do here is we can impose a coordinate system on this. So let's say that right in the center here, let's say that that's, my point 0, 0, right? And so what do we know, right? We know that this distance here is C, right? Negative C. And then we would know that this over here is negative A, and we know that if we go up here, I continue the coordinate system, that this is up here at B. Right? A is the distance from the center out to the vertex, and then here is where we cross the minor axis up here. All right, so with all of this, we can think about what are A and B. Well, because the walls are 50 feet apart, we know that it's a total of 50 feet from here to here. And so that must mean A is equal to 25, right? And then we know that this height here is 15 feet. So that must mean B is 15. Well, if we know A and B, then we can figure out C. So we know that C squared is equal to 25 squared minus 15 squared, which means C squared is 400, So C is 20. So if C is 20, of course, then that's 20 here and 20 here. So that means they are standing 40 feet apart. All right, which is pretty good that you could whisper to somebody who's 40 feet away from you, and then they could hear you perfectly. So it's kind of a cool little problem. In various cities, you can find these whispering galleries. All right, so the main focus, though, of this particular video is to take what we learned about ellipses in the first video and then shift them around, right? Make it so that the center isn't necessarily right at the origin. So I create this picture here and give you all these facts where, first of all, the center you're going to look at just like you did with equations of circles, right? It's x minus h, y minus k, where hk is the center. But what I want you to really focus on here is don't try to memorize all these things. Here's what I want you to think, okay? In fact, going back to that previous page for a moment, right? We know that A is how far from center you are on the major axis. B is how far from center you are on the minor axis. And C is how far from center the foci are. So think of it just like that, okay? A, B, and C still mean the same thing, except for now, instead of saying how far they are from the origin, now we're just saying how far they are from the center. So, you add C or you subtract C, in this case in the x value. You add A or you subtract A from the x value of the center. And then I'd also put this here. Remember that when we're talking about an ellipse that's longer vertically than it is horizontally, then what we do is we put the A underneath the y value and the B underneath the x value. But it's just still the same thing, right? The focus is either a C above the y value of the center or C below the y value of the center. And same thing with A and B like we described in the last picture. So try not to think of this as, oh, there's all these points I got to memorize. Don't do that. Just try to focus on everything in relation to the center. All right, and let's look at how we can put this into practice. So it says, find the equation for the ellipse with a center of 2, -3, vertices of -8, -3, and 12, -3, and foci -4, -3, and 8, -3. Now, if you just stare at these 5 points for a while, you could probably eventually figure out exactly what's going on here. But I highly suggest go ahead and start sketching these things out, even if you're not asked to make a graph. So I'm going to begin by just making some axes here. And don't worry about being really accurate in this graph. Just kind of look at what we've got. Notice that the y values are all -3. So I'm just going to go down here and call this -3. Right? I'm not worrying about being overly accurate here. And then I've got all these different x values, right? So it looks like the smallest one's -8, and the largest one's 12. So I'm just going to go ahead and do this. Let's go ahead and count by 4s. So we'll call this -4, -8, -12. And then 4, 8, 12. And I'm just going to go ahead and plot all these points. So 2, -3 would be right here. -8, -3 is here. 12, -3 is here. -4, -3 is here. And 8, -3 is there. Right? So we know that this one's the center, right? these are the foci, and then these are the vertices. And so that really kind of, for me, helps me get settled here, right? So if this here is the center, then I can start to make sense out of what A and what C are. So I know that A, right, is the distance from the center out to this vertex. And so so A is equal to 12 minus 2, which is 10. So when thinking about this formula, right, remember what we're trying to make here. Notice that the major axis is horizontal, so that means I know that the A is with the X, the B is with the Y. All right, we definitely know our center, right? Our center is 2, negative 3. Okay, and we've just identified our A, right? So this will be 10 squared right here. Now, we don't know our B yet, right? Our B is how far we go up the minor axis. However, we do know what C is, right? C is this distance. So 8 minus 2 is 6. So since we know C is 6 and A is 10, we can solve for B using this formula here. So we have 6 squared equals 10 squared minus B squared. So 36 is 100 minus B squared. So we get negative 64 equals negative B squared. So 64 is equal to B squared. And that's enough right there, right? Or you could also say 8 equals B, right? So 8 squared goes right there. And then just to put it all cleaned up, so this would be x minus 2 squared over 100 plus y plus 3 squared over 64 is equal to 1. All right, so for me, the key to this, and notice I didn't even bother to finish graphing this, although I could if I wanted to at this point. You know, I could go ahead and sketch in, you know, so B equaling 8 would mean I would go up 8 from here. So that'd be up at, I guess, like 5, right? And down here at negative 11, right? So you could, and then so you could go ahead and get a sketch of things like that. Negative 11, I think, is a little closer up here, right? And so if you wanted to, you could go ahead and sketch that out, but it's just really not necessary because you weren't asked to graph it. So we just do enough graphing up here that we're able to kind of get the ball rolling in terms of figuring out this equation. All right, let's check out another one here. This one asks us to find the equation for the ellipse with foci of 1, negative 4, 5, negative 4, and that passes through the point 3, 1. So this one we might find a little bit more challenging, but again, I would definitely start by sketching on a grid the information they gave us. So we got these 2 points, both at y equals negative 4. So just go ahead and say, call that negative 4. And we're at 1, negative 4, and 5, negative 4. So 1, 2, 3, 4, 5. So we got these 2 points here. Now these are foci, right? This is focus number 1. This is focus number 2. And then we have this other point, 3, 1. So that puts us right about there. Okay, the point 3, 1. So that's telling us a point that is on the ellipse itself, right? So you can kind of maybe sketch just a little chunk of it just to emphasize this is the point actually on the ellipse. All right. So we need to know, right, our center, since the foci lie along a horizontal line. I know that this is another one, like the last problem, where the A is with the X, the B is with the Y. All right, but at this point, we don't even know the center, right? They didn't tell us that. However, what we do know is that each focus has to be the same distance from the center as the other one, and that the y value of the center needs to match up with the y value of these two foci here. So I actually do know my center, right? The center must be 3, -4, right? It's got to be equidistant from those two foci. All right, so I can start to sketch that in. So it'd be x minus 3 squared and y plus 4 squared equals 1. But notice that we don't know what A is, and we don't know what B is. In the last problem, we at least knew what A and C both were, so we were able to find B. But here, all we know is C, right? So we do know, right, using, once again, our formula, C squared equals A squared minus B squared. What we do know is that because C is 2 away, or the focus here is 2 away from center, we know that C is equal to 2. So I can go ahead and put 2 squared in here. Okay, but that's all I can do. I don't know what A or B are. Okay. Now, the one thing we haven't used yet is this point 3, 1. We know that that is on the ellipse. So if it's on the ellipse, then I should be able to plug that in to this equation and solve for an unknown, right? Well, that potentially could allow me to solve for A or B. But we really don't want to have two different variables, right? We only want one. But this formula down here gives me a way to do that, right? So 4 is equal to A squared minus B squared. So that means A squared is equal to 4 plus B squared. So what I can do here is, instead of writing A squared down here, I can go ahead and put 4 plus B squared. And then here, of course, put B squared. And so now I only have one single variable to solve for. And then, if we plug in 3, 1, then we can solve for B squared. So I go ahead and put 3 in for X, and 1 in for Y. Of course, this one zeroes out, and so here we just have 5 squared, so that's 25 over B squared equals 1. So 25 is B squared, so that means B is equal to 5. And so then here I can say 4 plus B squared is 25 is A squared, so that means 29 is A squared, and that gives me my formula, right? So let's put this in red here so it's really clear that that's my final answer, since I'm kind of running out of space. So x minus 3 squared over 29 plus y plus 4 squared divided by 25 is equal to 1. So again, what got us started? What got us started was sketching the picture, and then I was able to get my bearings, find my center, and then use my formulas to figure out what A and B need to be. All right, so let's take a look at one more example here. This one's going to be more similar to some of those circle problems that you did, where you knew that the form of a circle we're all comfortable with is the whole x minus h squared plus y minus k squared equals r squared. But if a problem wasn't, or excuse me, an equation wasn't given to you in that way, you could make it look like that by completing the square. So that's our task in one like this. So I know that I'm comfortable if I can make my equation look like this. Then I know exactly how I'm going to graph this thing, right? And of course it might be, you know, this A, not that it really matters, but this A might be with the Y instead, right? So this is of course also valid. So we're not assuming we know ahead of time which way it's going to turn out. All right, so how do we go about this? Well, remember with circles, what we did was we began by putting the x's together and putting the y's together. So we'll start by rewriting this as 9x squared minus 36x plus 4y squared is equal to 0. Now remember when we worked with circles, if I had a coefficient other than 1 in front of the square term, I factored it out of everything before I tried completing the square, right? We always want to have a 1 in front of our square term when we try to complete the square. So as I look here at the x's, I would definitely want to factor a 9 out of there. But here's the deal. When it was a circle, the coefficient in front of your x and y squared terms would always be the same in a circle. It will not be the same in an ellipse. So you're going to factor 9 out, but you're only going to factor a 9 out of the x terms. Oops. You're only going to factor a 9 out of the x terms. And of course here, there's no factoring to be done, right? But if there were multiple terms there, I would factor a 4 out of that. And then of course with completing the square, we say, okay, I need to add something. In order to make this a complete perfect square. But on the right side, I need to also add that same thing. But be careful here, right? When you do add this, you're not only going to add what you put here, you're going to add 9 times that, right? And remember, because whatever you put here, because this 9's factored out, you're really multiplying it by 9. So on the right side, you need to add the same exact amount 9 times whatever that number is. All right, so of course here this is negative 4 divided by 2 squared. Negative 4 divided by 2 squared. So we get 9 times x squared minus 4x, and then this is negative 2 squared, which would be 4. And then 9 times 4 is 36. So here that factors into x minus 2 squared. All right, and now you'll notice that this is looking a lot more like what we're used to an ellipse looking like, right? Looks like this form up here. Okay, but there's one big difference, and that is up there we were dividing by something. Up here we're multiplying by 9 and 4. And also you'll see that on the right side here there's a 36. What do we want to be there? We want a 1. So in order for this to be valid, we need a 1 on the right side. And so how do we do that? Well, if we go and divide everything by 36, that would turn that into a 1. But what are the consequences of dividing by 36 on the left? 9 divided by 36 simplifies to x minus 2 squared over 4. And then y squared over 9. And so from here we should be able to graph this, right? So I can get them all, everything on the same part of the page here. Let me rewrite it. X minus 2 squared over 4 plus y squared over 9 is equal to 1. So of course the larger number is the a squared, right? So from this I can tell that a is equal to, well, a squared equals 9. So a equals 3. I can see b squared equals 4, so b equals 2. And so therefore I know c squared is equal to 9 minus 4, which is 5, so c equals the square root of 5. And the square root of 5, just so for the purposes of graphing, is about 2.24. All right. Now the a, the larger number, is with the y, so I know that the major axis is going to be a vertical axis this time. Okay. And then the last thing, in addition to a, b, and c, of course, what do I know? I know that the center is the point 2, 0. So as I graph this thing, let's see, we'll make tick marks about like that. So here's the center right here at 2, 0. Okay. And then my A, right, goes off of the center 3, and so that will give me my vertices. So we'll go 1, 2, 3 up from center, 1, 2, 3 down from center. So these are the vertices of the ellipse. Then my B, oops, that's off a little bit, isn't it? Then my B is 2 off center, but in the horizontal direction. And then my foci are 2.24 off center in the same direction that the vertices went. So 2.24, it puts me about there, puts me about there. And so now I can sketch this. Not too much trouble. All right, now I know our page is getting really full right now, but there is one other thing I want to do with this, and that is, we did this with circles, but I want to take the time here to remind you of, if I want to check my work in my calculator, how do I do that? Okay, so remember, what we have to do to check our work in the calculator is we have to get y by itself, right? So that way we can type things into our y equals menu. So let's see, over here, I'll do this in green. We'll just say to type in the calculator. So we'll take our equation and we're going to get y by itself, right? So first I can just take this whole mess and subtract it over. So we would get y squared over 9 is equal to 1 minus x minus 2 squared over 4. And then, of course, we could multiply both sides by 9. And if we did that, get some nice cancellation there. So y squared is 9 minus 9 times x minus 2 squared over 4. And then we, of course, want to take the square root. But remember, when you take the square root of a number, that's plus or minus. And you recall that with circles, the plus and the minus each give you half of the circle. So it's going to be the same thing here. The plus gives you half of the ellipse, and the minus gives you the bottom half of the ellipse. All right, so we can type that in our calculator, and let's just go ahead and do that here. So I would just type in these two equations. So the square root of 9 minus 9 times x minus 2 squared divided by 4. And the same thing, but with a negative put out in front. And then we'll go ahead and graph that. Okay. And if you're saying, well, that doesn't look much like what you saw on paper, well, yes, but that's because my scale is different. So if I wanted to really match up with the scale that I have on my paper, I would probably just graph from maybe about -5 to 5, right? Because I graphed, the ellipse only takes up 4 units in the x values on the positive side, and then I'd probably go, maybe -5 to 5 in the y's based on how I made my scale. Okay, and then that is going to look a little better. Remember, I know that this still looks a little bit strange, but I want you to remember that the spacing between x values is different than the spacing between y values, right? So if you wanted to make it a little bit more true to how it might look when the scales were consistent, remember, one thing you can always do is hit zoom square, and then now it's more elongated like it is on the picture that we just drew. All right, let's do one last example here. There's nothing really new here, although maybe you might find some parts a little more challenging. So I would encourage you to try this one on your own before we do it together. Maybe hit pause, and then we'll come back and see if we get to the same thing. Okay. So let's work this one out here. So we've got 2x squared plus y squared equals 2y plus 1. So first thing, we want everything on one side of the equation, except for that 1, of course, but all the y's on the one side of the equation. All right. So we don't have to factor anything out of the y, and that's nice. And then the x squared doesn't need to have its square, or excuse me, we don't have to go through completing the square there, right? Because it's already a perfect square. So we can leave that one alone and then just concentrate on saying, well, what do I add to both sides, right? But we know we're going to add half of the middle term squared. So we end up with 2x squared plus y squared minus 2y plus 1 equals 1 plus 1 is 2. So 2x squared plus y minus 1 squared equals 2. But of course we know that we need to have a 1 on this right side. Go ahead and divide everything by 2. So that gives us x squared plus y minus 1 squared over 2 equals 1. So we can see here that a squared is 2, so that means a is the square root of 2. We can see b squared, well, there's nothing there, but of course there's really a 1 right there. So b squared equals 1, so that means b equals 1. And then we can see that c is going to be a squared minus b squared, so 2 minus 1, which is 1. So we've got all these nice small values, right? And then of course our center is 0, 1. So this is one of those where it would be really good to think ahead about your scale. All these numbers, A, B, and C, are very small. The center's only at 0, 1. So as I create my scale here, what I'm going to do is just maybe do this. All right. So each of these is just 1. So my center is right here at 0, 1. My A goes square root of 2 in either direction from here, right? Square root of 2 is 1.41. Let me scroll back down here, right? a equals root 2. Yes, we like exact values, but we also want to know how to get this thing graphed. So that's 1.41 when we put it in our calculator. So what that means is from center, I should go 1.41 in this direction and up 1.41 in that direction. All right, and then as far as my B goes, remember my B is just 1 in either direction. So from the center I go here, and from the center I go here. And then lastly, the foci, right, are 1. So from the center in the direction of the vertices, we go up 1, down 1. And so that right there gives me my picture. And you can see the lack of symmetry here is just due to my not quite getting my scales consistent, right? Not quite getting my the distance between x's and y values. In fact, you can see it here, right? The distance from 0 to 1 is kind of different than the distance between 1 to 2. So that's why it kind of looks a little more elongated up top. But got all the important features on there, so that'll be good enough.